Oh, okay. It's just like,
And then it was like four.
Okay. I'll have to work on getting this pointer to actually click us through. For now, it'll just be my little laser pointer. Welcome back. So today we're going to be talking about the beginning of the Earth so that we can get rolling and eventually actually get to life. Tomorrow, Wednesday. Wednesday is tomorrow for us, I guess. First of all, who wants to colonize Mars? Anybody want to colonize the moon? At least two friends say that they would move to the Mars colony, even knowing that they'd never come back. I worry about them sometimes. should set a reminder to check in. But you know, we need explorers, right? Okay. So we're going to go through the basics of Big Bang, how we got to having an Earth. If you have very detailed questions about this, I recommend going and talking to Dr. Tyler in the physics department. He's actually an astrophysicist. Here he's an expert in the aurora borealis and is sometimes interviewed on TV about that. Which is really cool. But this is my disclaimer that I am not an astrophysicist, but I'm gonna walk us through the basics as best I can. Okay. So we're trying to figure out how we have the starting materials for our planet, how we have our baseline that we're gonna build up from throughout the rest of this course, throughout the rest of time. Okay. So we are going to start with the origin of the universe. Okay. So our current understanding, our current theory that explains the data that we see thus far is that all of a sudden there appears the whole universe as once as a single, very dense, very hot point. Scientists don't know what happened before this, if there was a before. That's a little bit subject to lots of debate about why this happened, how this happened, what this means. But that's where we're starting from. That's what we have data about, we think, thus far. So after a teeny tiny bit of time, 100th of a billionth of a trillionth of a second, a trillionth of a trillionth of a second, this starts to expand. So that is something that we can also see. We can see evidence of the expansion of the universe because we can see galaxies actually moving away from us. Okay. So this started very soon after the appearance of that point. That is our Big Bang. It's not so much two things colliding or an explosion, although we sometimes think of it that way. It's really about this appearance and then the expansion. Now, as things expand, they get cooler and less dense. It's kind of thermodynamics, but you can sort of intuitively understand this. As things get farther and farther apart, they're holding together less energy, they're spreading out. So as our universe is expanding, everything in it is cooling down, and since we're filling up less space, we have lower density. At a certain point, when it gets cool enough, matter starts to form. And in terms of matter, the first things that we see forming, or the first things that we can calculate formed, are hydrogen and helium. So the first elements that we start to see. Over time, the elements that are forming, the matter that's forming, starts to clump together. And at this point, it's in the form of gases. It starts to form stars, starts to form galaxies. So here we have a sort of timeline of the creation of the universe. So we're running the top from point 0, our point sphere of infinite density, super hot. to today, and our current calculation is about 14 billion years. The current estimate is like 13.7, but we've got room for error on that number. Right? So here we start to see the heat dropping until we actually live in a very cold universe right now. At the beginning, we see our radiant energy and our electrons and neutrinos running around, forming protons and neutrons, creating our first stable elements and creating atoms. And then we get our galaxies, our stars, and our solar systems. We said we're going to talk a little bit about evidence. So two of the main pieces of evidence that we started out with, that we use kind of the Big Bang Theory to explain why we see these phenomena, are they noticed as far back as the 1920s that galaxies are moving away from Earth. And we can measure that speed of the galaxies moving away. And they actually noticed that objects that are moving or that are farther away from us are actually moving away from us faster. So this is evidence for expansion, and evidence for expansion comes everywhere. Right? Close things are moving away from us, but farther things are moving in even faster because all the objects together are moving away from each other, is the understanding of why we see this movement. So this is first recorded by Hubble in the 1920s. Same guy that the Hubble telescope is named after. His original estimate, though, is only 2 billion years. So we spoke on Friday as a kind of orientation here, that our goal in this class is to kind of think about evidence, think about facts, approach them with skepticism, and realize that science is in itself an evolution. We're revising and revising theories, revising and revising our understanding as we find new data. And if our old theory doesn't work, we make a new one. We're maintaining skepticism and creativity. This isn't all settled all the time. It's just the best we can do to understand what we see. So Hubble's original estimate was that our universe was 2 billion years old, but the current data, we're all the way up to 13.7. So this partially has to do with new technology. We've taken new pictures, we have new instruments that can more accurately measure that speed. And we also have other pieces of observable data that we now can integrate to find sort of different pieces of corroborating independent evidence for this theory. So just a note about that speed thing. So what he was actually looking at when he saw that galaxies were moving away, right? It's not like there's a speedometer. It's not like it was just getting smaller and smaller. It's like, oh, it must be speed. So the term for what he saw was redshift. So this is explained partially by the Doppler effect. So if you've heard an ambulance that goes, but then once you're behind it, it sounds different, right? And this is because the apparent wavelength of a sound, but also of observable light, would change whether it's approaching versus when it's going away. Okay. So he notes this red shift in its images of the universe and of the galaxies. So everything is kind of shifting, basically a different color. And this is dependent upon how far things are away. So this is his actual sort of data of the distance versus the velocity. The second big piece of evidence that people like to talk about is cosmic microwave background radiation, CMBR. As you can see, these two starter pieces of evidence that they include in textbooks are pretty old. So in the 1960s, they were studying radio signals, a little bit to do with satellites and how they were potentially able to bounce radio signals around and off them. And they were studying this in New Jersey, and they started to find interference with their radio signals. So we like to use Occam's razor, right? We like to find the simplest explanation for things that we can as scientists. So their first thought was, we're in New Jersey, it's probably just interference from New York City, it's kind of close. But as they took more observations and as more scientists took more observations, they realized that this radiation could be found everywhere in all parts of the sky, day, night, basically observable throughout the entire universe. So it was probably not New York City affecting the entire universe everywhere. So they named this observation of this radio interference, this radio noise, basically, that we see, the cosmic microwave background radiation. And they saw that it was coming actually from beyond the Milky Way, so from beyond our own galaxy. And it's been interpreted as essentially leftover heat from the Big Bang. That single point originally was super dense, super hot. We can still see some of that heat. Didn't put it in the slides, but more recently, we've started to talk about dark matter, dark energy, and we have basically inferred that from similar principles. I think a fair bit of it has to do with this expansion bit. So we can see the effects on gravity, and we can see sort of the effects in the expansion. But I absolutely am not a dark matter expert, so subject for another class. Okay. So that's what we got so far for a universe expanding. We have gases forming, atoms forming, and starts to clump together. So we can actually watch solar system formation far away from us through telescopes. So we can see this sort of thing happening elsewhere. So that is mainly where this solar system formation theory kind of comes from. So the going understanding of how a solar system forms is something called the nebular hypothesis. So our baseline, we start out with a large gas cloud or a nebula that begins to condense. Okay. So as these gases are condensing, solid, becoming more dense, most of the mass moves to the center. Most of the mass is in the center, really, and around the edges, we have some turbulence. So there's some movement around the edges here of this gassy cloud. Okay. And that's where matter is starting to collect, collide, and clump together. We have gravity, so the gravitational attraction is starting to cause everything to sort of pool, slowly contract and pool, and then this forms as a disk that starts to rotate. And as this is happening, think of like kind of a whirlpool. So dust and matter are slowly falling towards the center of this cloud. So in the center, we have the formation then of the sun, where all this gaseous matter is condensing. And around the edges, we do still have some more grains colliding together in small chunks. And they have their own gravity as well. So some of them start to aggregate more matter and eventually become planets. Okay. So that brings us to the Earth. So the Earth, our current estimate is that the Earth formed approximately 4.5 billion years ago. We're scientists, so we have an error range on that, and our current estimated error range is about 50 million years. Okay. So this number took them a while to get to. So usually we trace this back to about the 1800s with Lord Kelvin, who estimated an age between 200 million years and 400 million years for the Earth. Now, what he was basing this on was the idea that the Earth started as a molten mass, so started hot, started kind of liquid. And he calculated how long it would take to cool to be what we see today. So you can also see he had a big error range on his own estimate. Our current estimate is not within that number, but that's okay. That's how science works. Okay. So what kind of data do we use to look at this age? Why have we revised it? So this brings up one of our geologic principles that we will come back to throughout this course as we think about things like fossils and dating those. Okay. So fundamentally, this works the way essentially a really messy deck does. All right. So the basic principle is just that the oldest stuff is on the bottom and the youngest stuff is on the top when we're looking at layers of the Earth, when we're looking at layers of the crust, layers of rock. All right. Now, this doesn't mean you didn't at some point pick up some really old thing because you thought it was important and move it to the top, or shove some young thing down to the bottom. So you can think about mountain ranges coming up. You can think about plates moving against each other and taking top layers and moving them under another tectonic plate. But we can see those cross cuts kind of across a bed that is layered in a somewhat orderly manner. So the principle of superposition is just basically stating this, that when you see things that are in a newer layer, a layer on top, that's younger. When you see things on a lower layer, if you have to dig deeper, that's an older layer. So one of the ways they first started seeing this was they were trying to figure out why they were seeing super old, basically deep sea fossils on the tops of mountain ranges. So they realized that these were kind of picking up old layers, moving them to the top potentially. Also that we have different geography now than we used to. So this doesn't give you an exact year for dating anything, but it tells you what layer to look at if you're looking for something really old, basically. So you have to find all the things that were deep down and try and get to those. What does give us actual numbers is radiometric dating. So the way radiometric dating works is that we have our elements. They have some different variations based on the number of neutrons in their nuclei. So not all atoms, not all elements are stable. And we can actually observe this. We can observe that unstable radioactive elements do decay into more stable elements over time. And that time is measurable, and we measure it in half-life. So half-life is just the amount of time it takes for half of the quantity of that element to decay from its unstable form to its stable form. So when we're dating samples of rock, of soil, what we do is we look at these isotopes and we look at the ratio of that original parent unstable isotope to the daughter isotope. And if we know the half-life of that element, the half-life of that isotope, we can then calculate how long it's been decayed. So that's the basic of how radiometric dating works. Is we're looking at the proportions of these elements. So you can see as half-lives pass, after one half-life, we have half of that radioactive part left, another half-life, half of what was remaining, and so on and so on and so on. And this can take a very, very, very long time. Right. So using some of these techniques, the oldest rocks we found are about 3.8 billion years old. Some tiny minerals, rocks and minerals are different, are about 4.2 billion years old, but our current estimate for the age of the Earth is 4.54. So why might that be? We got some more data, right? So that's not all we have. So another thing that we've learned about how rocks work on Earth is that they're part of a rock cycle. It's pretty funny to me. It's kind of funny name, but rocks shift between different forms. So over time, rocks shift from igneous rocks to metamorphic rocks, sedimentary rocks, and we have moving plates, right? So we'll talk about plate tectonics later because we'll be talking about continents and how they move. But basically, we have our plates shifting around on the surface of the Earth. So we do have old rocks that are sliding back down into the Earth and into the mantle. At the same time, through volcanic activity, we have new rocks forming by lava, so bringing up things from deeper down. Okay. So it's not so simple to find the oldest possible rock. Never mind that someone really has to walk out there and take it up and test it. Now, what they came up with to get around this problem is to look at meteorites. So the rock cycle is a process that we see on Earth, but the moon doesn't work the same way. The moon doesn't have a rock cycle going on. We don't have the same shifting of plates and this movement. And we kind of know when the moon formed relative to the Earth. What they did was they went to the moon and they found meteorites there and then dated those. And that's how we get that older date, actually, of 4.5 billion. So we will be talking as we move forward about geologic time. Not too concerned about it here in this essentially astronomy portion, but I want to show you essentially where we are so we can look at the order of events. So eventually we are going to get all the way to the modern day. But here we're starting way, way, way back. Okay. So this geologic timescale is showing us the order of events beginning with when the sun forms and the accretionary disk. So basically the floating junk around it that is eventually going to condense into climate. So we have that long, long ago. Here we have the planetesimals accreting and the Earth starts to form, starts to pull all its stuff together. Then we have the formation of the moon. Then we have core formation. Then we have our oldest mineral grain. And then as we move forward, we can start to see that we have bombardment by other planetary bodies. So basically, we're going to see that the Earth collided with a bunch of stuff. And then we're going to start to get to water. So this is why it was helpful to look at moon rocks, essentially, because the moon is forming basically as the Earth is forming. So for the first 500 million years, the surface of the Earth gets hit by asteroids and comets all the time. We don't have an atmosphere at this point to burn up these things like asteroids. So they're all just kind of pell-mell hitting the surface of the Earth. One of them hits so hard that the moon breaks off. So this is called the giant impact hypothesis, that about 50 million years after the Earth starts to clump together, after the creation of the Earth, a planet about the size of Mars hits the Earth. Right? So something really, really, really big. Okay? Now, it took a while to do any kind of tests about whether this was even possible, but based on modern high-speed computers, it's not impossible, right? So it's not proven, it's not disproven. Okay, so this is the event that we are expecting formed the moon. Now, it didn't just form the moon. So a bunch of stuff got blown off all the way into space. So we have this huge thing hitting the Earth. All right, we can see that a bunch of stuff is blowing open, breaking off. A bunch goes into space. But then some of these chunks are being pulled back into the gravitational field of the forming Earth. And those pieces that got stuck there in that gravitational field remain. So eventually this coalesces into the moon. It started out as being very close to the Earth, but over time has gotten farther. So thinking more about the early Earth. So the early Earth underwent some heating and melting in the interior. So part of this was due to collisions like that big one from protoplanet almost the size of Mars. So those collisions create heat from that impact energy. So does compression as things are pushed together. We've also mentioned that one of the ways that we're dating rocks is by looking at radioactive elements in decay. So that radioactivity of those elements itself is putting off heat. So this is how we get to the point where we have melting essentially in the center of the Earth. So 400 to 800 kilometers below the surface, we reach the melting point of iron. So this is part of why we start to see layers in the Earth. So if you've ever been to a science museum, I'm sure you've seen something like this, right? That shows you the layers in the Earth. So we have different distribution of the elements that form the planet in different layers. And this is different than our sediment layers when we're talking about fossils. This is way, way deep down, too deep for us to get to. But we start to see that we have heavier elements like iron moving down and sinking into the core of the Earth, and lighter things like oxygen and silica are floating up towards the surface. So you can think of it kind of like a centrifuge thing, except maybe in the reverse. So this finishes, we think, about 4.3 billion years ago and leaves us with an inner core, an outer core, a mantle, and a crust. Okay, so here we can see that we started out with a bunch of iron, molten iron, ending up towards the center, lighter things out on top. Okay, and then we're solidifying into a solid iron inner core, surrounded by a liquid iron outer core. Then we have the mantle, which is super thick, and then the crust. So for the purposes of this course, we are almost exclusively going to be thinking about things in the crust. We cannot get all the way deep down to the core of the Earth to observe it. Certainly, as far as we know, there's no life down there. So each of these layers does have a distinct chemical composition though, which is worth knowing as we start to think about why do we start to see the formation of life. So the crust is actually quite different in composition relative to what you would get if you measured the entire Earth. And that's because we've had that sort of separation by mass, essentially, by weight, right? So we have lots and lots of iron if we measure the whole Earth. Honestly, here on the banks of Lake Superior, it seems like there's a lot of iron here too as well. But for the most part, most of that iron has sunk down towards the core. This leaves us with our lighter elements on the crust, lots of silicon, lots of oxygen, as well as other trace elements. So we have some aluminum, we have a little bit of the iron left, magnesium, calcium, potassium, sodium, and other things. We could also name layers according kind of to their chemical composition. So out in the lithosphere, that's our strong, rocky outer shell of the Earth. So that would include the crust and parts of the mantle. Then below that, in the deeper parts of the mantle, we have a ductile, so a flexible layer of the mantle. And this is the part that's going to deform in shape. So it changes in shape as we have motions of tectonic plates and stuff on top of it. That's why we're able to have that motion, really, is because there's something flexible underneath. The deep mantle continues below it. Then we get to the core. The outer core is liquid, and then the inner core, we think, is made of solid iron. So all these things together are part of what's giving the Earth its gravity, giving it its mass, giving it its ability to hold things. To get to continents, we then start to think about volcanism, essentially. So we're thinking about magma. So I'm gonna flip back 1 second. All right. So our inner core, solid iron. We have our liquid shell of iron in the outer core. And then the mantle has different parts, right? Some of which are flexible and some of which we kind of associate with the crust. Okay. So in that mantle, though, we have basically magma, right? So it's part of that flexibility from that heat, from that molten state. And we start to have some of that thrown up and out, right, where it cools. So this is how new rock often forms, is from solidified magma, so solidified, formerly liquid material. Okay, so here we can see that molten rock spewing up and out, landing in the ocean where it cools. This is the idea of part of where our continents form from, how we end up with that sort of different distribution on the surface, that geography. And the oceans and the atmosphere are also associated with that volcanic nature of the early Earth. We have lots and lots of volcanoes. We have lots of this happening everywhere, as far as we can best understand. Okay. So this is part of how we start to get the gases that we see in the atmosphere. So the molten rock is falling back and cooling from a solid rock, but we also have outgassing of hydrogen and nitrogen and carbon dioxide, which are kept held in by the Earth's gravity and start to form our atmosphere. So originally, part of why we were getting hit by all those asteroids and comets is that our atmosphere was really thin, primarily helium and hydrogen. Right? If you think about the moon, right, you can see all those craters on it. It didn't really have much of an atmosphere. So lots of stuff hits it and leaves those pock marks. So that helium and hydrogen, we couldn't really hold on to all that well. They easily escape to outer space. Today, we don't see much of them at all in the atmosphere. Instead, it's these gases that we saw through these volcanic eruptions that we primarily observe, in addition to oxygen, which is actually tied in to our evolution of life that we'll be walking through. So this volcanic outgassing is creating a thicker atmosphere. A thicker atmosphere and also a varied atmosphere, because it's pulling out all the things that are swimming around there kind of in the mantle. So we think that the gases that got released are probably similar to those created by modern volcanic eruptions. And we think that's because that's what we can observe. And so we work that into our theories. Okay. So that's how we kind of get our ideas about the proportions there. So we think that this would include water vapor, sulfur dioxide, hydrogen sulfide, carbon dioxide, carbon monoxide, ammonia, and methane, but actually not oxygen. So we're going to think about changes to the atmosphere over the history of life and how actually the presence of life on the planet is part of why we see the proportion of gases in our modern atmosphere. To get our ocean, this is also related to those volcanic eruptions. So that is hypothesized to come from the water vapor that is being spewed out by the volcanic eruptions. So over hundreds of millions of years, that water vapor coming out of the eruptions as gas is also cooling and condensing and forming oceans, in addition to what we mentioned about continents. Also, comets are often made of just big chunks of ice. So as we're getting pummeled by all sorts of space junk, right, meteorites, asteroids, we're getting pummeled by comets. The Earth at this point kind of hot. So when these balls of ice, these comets hit the Earth, this can also be potentially one of the major sources of water that formed our ocean. And when the comet hit us, the ice melts and we keep that water. So the earliest evidence that we have of water on the surface of the Earth is about 3.8 billion years. And this is from looking at rocks, and we'll talk about this next time as we start to talk about the first life, because water is really important to our Earth's life forms. Okay. And we also want to think just about what else is in that ocean, what else is in that surface water. So we have a lot of dissolved elements, including iron. So that iron has settled towards the core, but we are still leaving some of it on the surface. So we're moving forward towards our evidence for water. So we have our atmosphere that is forming, as well as our water, our continents from all this off-gassing from volcanoes. Right? So the early atmosphere would not have been great for life as we know it. Major components are carbon dioxide, methane, water vapor be okay for us, but we definitely don't have practically any oxygen. So this would be a very toxic planet for us ourselves to live on. We operate under a baseline of about 21% oxygen, and we're not super flexible about that, really. People get altitude sick, they even climb up to really high mountains. So this would not work for us. Like, lots of things have changed about the Earth over time. So part of it is atmosphere. We'll also walk through lots of temperature changes that have happened over time. We're going to see a lot of shifting, sort of back and forth between the geology of the Earth, weather patterns, and what we actually see on the surface, including water. So we're gonna actually just do this in class right now. So what I'd like you to do is to dig into a little bit of evidence yourself. So we want this class to be focused on just like evaluating different types of evidence so that you can keep evaluating evidence, keep evaluating new theories as you move forward in your real lives. So I want you to go ahead and find the quote unquote best conspiracy theory about Earth and its geology. And whether you want to choose best to mean most convincing or weirdest or funniest, it's up to you. So I want you to go through and I want you to find one, and I want you to find what facts are used in favor of this conspiracy theory, alternate theory. And I want you to find a source for facts that oppose this as well. And then we're going to kind of evaluate where those sources are from, what their biases might be, whether you could go observe those things or not, right? Because we want science to be, at least in theory, reproducible if you had all the multi-billion dollars. Okay, so this is now classwork and not, yeah, no home.